A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
So, I was looking at the infrastructure spending reports from this morning, and it is official. We have fully crossed the Rubicon. As of this month, March 2026, more than half of every dollar spent on AI is now going toward just keeping the lights on. We are finally in the deployment era where running the models is more expensive than training them.
Corn Poppleberry here, and you are hitting on the fundamental shift of the year. For so long, everyone was obsessed with the training phase, the massive clusters of H100s grinding away for months. But now that these models are actually being used in production at scale, the focus has shifted to the efficiency of the inference itself. It is no longer about who has the biggest cluster for training. It is about who can serve the most tokens per second for the lowest cost.
Which brings us to today's prompt from Daniel. He wants us to dig into the technical reality of the AI runtime. It is that critical software layer sitting between the hardware and the model weights. And honestly, it is the piece of the puzzle that determines whether your application feels like a snappy conversation or a slow crawl through mud. It is the unsung hero of the AI stack.
It is the most overlooked part of the entire stack for people outside the engineering room. When you download a model from Hugging Face, you are getting the weights, which are basically just a massive static file of numbers. They are the brain in a jar. But that brain cannot think until you have an engine to process those numbers. That is the runtime. It is the active software environment that loads those weights into memory, manages the GPU kernels, and orchestrates the mathematical operations required to turn your text into tokens.
I think a lot of people assume that if you have the weights and you have a beefy GPU, the rest is just magic. But you are saying the runtime is actually the nervous system that makes the brain functional. Without it, those weights are just dead weight.
Think of the weights like a musical score. It is all there on the paper. The notes, the rhythm, the structure. But the score does not make a sound. You need the orchestra, the instruments, and the conductor to actually turn that data into music. The runtime is the entire performance. And the reason we are seeing this massive spike in inference spending, over 55% of all AI infrastructure spend, according to the latest Unified AI Hub reports, is because we are realizing that the runtime is where the performance battle is won or lost. If your conductor is slow or your violinists are out of sync, it does not matter how good the score is.
So let us get into the weeds then. Why are there so many of these things? If I'm running a model locally, I'm probably using something like Ollama. But if I am looking at a cloud deployment, I am hearing about vLLM or TGI. Why can I not just use the same engine everywhere? Is it just a matter of preference, or is there a deeper architectural reason?
It comes down to what you are optimizing for. If you are running locally on your laptop, your biggest constraints are ease of use and hardware limitations. You might only have 16 or 32 gigabytes of VRAM. Runtimes like Ollama are built on top of the llama.cpp library, which is a masterpiece of engineering for consumer hardware. It uses a format called gguf, which is a single file format that includes both the weights and the metadata. It is designed to be portable and simple.
And gguf is the one that lets you do the offloading trick, right? Where you can shove some of the model onto your system memory if your GPU is too small. I have used that to run 70 billion parameter models on a machine that definitely should not have been able to handle them.
That is the core advantage. It allows for flexible offloading between the CPU and the GPU. It is designed for the single user. It wants to get that model running with one command, even if you are on a Mac or a Windows machine with a mid-range card. But that convenience comes at a cost. You are usually optimizing for latency on a single stream of text. You want the words to appear quickly for you, the one person using it. You are not worried about 10,000 other people trying to use your laptop at the same time.
Right, but that does not work if you are a company trying to serve 10,000 users at once. You cannot just run 10,000 instances of Ollama. That would be like trying to run a city's power grid with 10,000 individual camping generators.
You would go bankrupt in a week. That is where production-grade runtimes like vLLM come in. Developed at UC Berkeley, vLLM is built for high concurrency. Its claim to fame is something called paged attention. In traditional runtimes, the KV cache, which is basically the short-term memory the model uses to remember the beginning of your sentence while it writes the end, is very fragmented and wasteful. It is like having a bunch of half-empty notebooks scattered across your desk.
I imagine that waste adds up when you have hundreds of users hitting the system simultaneously. If every user is taking up more memory than they need, you run out of space fast.
It is a disaster for memory efficiency. Paged attention treats the KB cache like virtual memory in an operating system. It breaks it into small blocks that can be stored non-contiguously. This allows vLLM to pack way more requests into the same amount of GPU memory. The throughput difference is staggering. If you look at the March 2026 benchmarks from Particular Tech, switching from a basic runtime to vLLM on the same hardware can give you up to a 16-fold increase in throughput.
16 times? That is not just a small optimization. That is the difference between needing 1 GPU or 16 GPUs to handle the same traffic. I can see why the cloud providers are obsessed with this. But what about the weight formats? You mentioned GGUF for local stuff, but what are the big boys using? Does the format itself change how the runtime behaves?
In production, you are usually looking at Safer Tensors, which is the Hugging Face standard. It is designed to be secure and incredibly fast to load, because it uses memory mapping. But you also see specialized quantization formats like AWQ or GPTQ. These are ways of compressing the weights, turning 16-bit numbers into 4-bit or even 2-bit numbers, so they take up less space without losing too much intelligence. Different runtimes have different levels of support for these. A runtime like vLLM is highly optimized for AWQ because it plays well with their memory management system.
It is interesting that the same GPU, let us say an RTX 4090, can support all of these. I could run Ollama for my personal coding assistant in the morning and then spin up a vLLM instance to test an API in the afternoon. It is the same silicon, but it is behaving completely differently. It is like the hardware is a chameleon.
Because the runtime is using different kernels. Think of kernels as the low-level code that tells the GPU exactly how to do the math. A runtime like NVIDIA's Tensor RTLLM is the extreme version of this. It is a close-to-the-metal engine that uses kernel fusion. Instead of doing step A, then step B, then step C, it fuses those operations into a single massive step that stays on the GPU's fast memory. It avoids the bottleneck of moving data back and forth between different parts of the chip.
That sounds like the kind of thing that is great if you are locked into NVIDIA, but maybe a headache if you want to be flexible. If I spend all my time optimizing for Tensor RT, am I stuck with Team Green forever?
That is the ultimate trade-off. Tensor RTLLM will give you the absolute lowest latency on a Blackwell or Hopper chip, but you are married to NVIDIA. If you want to move that model to an AMD chip or an Intel accelerator, you are starting from scratch. You have to re-optimize everything.
Which leads us to ONNX, the Open Neural Network Exchange. Every time I hear about it, people call it the universal translator of AI. Is that still the case in 2026, or has the industry moved past it in favor of these hyper-optimized, hardware-specific engines?
It is still the go-to for portability. If you are a developer and you want your model to run on a wide variety of hardware without writing custom code for every single chip, ONNX is your best friend. But, and this is a big but, you almost always pay a performance tax. You are choosing a common denominator. You are not going to get that 16x throughput boost or the deep kernel fusion of a hardware-specific runtime. It is a choice between flexibility and peak performance.
It sounds like the classic engineering problem. You can have it fast, you could have it cheap, or you can have it compatible with everything. Pick two. If you want the speed of Tensor RT, you lose the compatibility of ONNX. If you want the ease of Ollama, you lose the throughput of vLLM.
If you're building an edge device like a smart camera or a local robot, you might go ONNX because you do not know exactly what chip will be in the final hardware. But if you are Databricks or Snowflake, you are going to squeeze every drop of performance out of the hardware you own. You are going to go as close to the metal as possible.
Speaking of Databricks, I saw they just integrated the new RTX PRO 4500 Blackwell chips into their serverless runtime last week. They are specifically targeting what they call agentic AI. Why does the runtime matter so much for agents compared to just a regular chatbot? I mean, a token is a token, right?
Not quite. Agents are autonomous. They are not just waiting for you to type. They are constantly thinking, planning, and reacting in the background. They might be running loops where they generate a thought, check a database, generate another thought, and then take an action. That requires a runtime that can handle continuous, low-latency reasoning without breaking the bank. If your agent takes 5 seconds to decide its next move because the runtime is inefficient, the user experience falls apart. It feels like talking to someone who has to look up every word in a dictionary before they speak. Databricks is trying to minimize that overhead by tightly coupling the hardware signals with the inference engine.
It reminds me of the announcement from F5 and NVIDIA about their Big IP Next system. They are using something called dynamo runtime signals to route requests. If I understood that correctly, the network itself is now talking to the runtime to decide which GPU is the most efficient for a specific request in real time. It is like the traffic lights are talking to the car engines to optimize the flow of the whole city.
It is a 40% increase in token throughput just by being smarter about routing. We are getting to a point where the runtime is not just a siloed piece of software. It is part of the broader infrastructure fabric. It is talking to the load balancer. It is talking to the Kubernetes orchestrator. It is providing telemetry that we never had before.
And that brings us to the big news from today, March 25th, 2026. The Cloud Native Computing Foundation just published the Kubernetes AI Requirements, or KAIR, version 1.35. This feels like a major milestone for standardizing how these runtimes actually live in a cluster. We have been waiting for this for a long time.
It is huge. Before today, trying to scale something like vLLM across a distributed cluster was a bit of a dark art. You would run into resource deadlocks where one node thought it had enough memory, but the KV cache would spike and crash the container. KAIR provides a standard interface for runtimes to report their actual memory pressure and throughput capacity to the Kubernetes scheduler. It is like giving the scheduler a real-time map of the city's traffic instead of just a static list of roads.
So the scheduler actually knows that vLLM is doing its page attention magic and can pack more work onto that node without it blowing up. It can see the virtual memory of the GPU.
It makes Inference a first-class citizen in the cloud-native world. We are moving away from the era of bespoke, hand-tuned AI servers and into the era of standardized, scalable inference fleets. This is what allows companies to treat AI models like any other microservice. You can spin them up, scale them down, and move them around without worrying about the underlying hardware quirks as much.
I love that term, inference fleets. It makes it sound much more industrial, which I guess is where we are. We have gone from the hobbyist playing with llama.cpp on a laptop to these massive automated fleets. But for the listener who is trying to decide what to use today, how do they navigate this? If you are a developer sitting down to build an app, where do you start? We need a decision matrix.
I think you have to look at your user count first. If you are building something for yourself or a very small team, do not overcomplicate it. Use Ollama. Use the GGUF format. The ease of setup is worth the performance trade-off because your time is more expensive than the extra milliseconds of latency. You can get a model running in 60 seconds. That is a huge win for productivity.
And if you are looking at an actual product, something with users who expect a fast response, and you do not want your cloud bill to look like a phone number,
then you have to look at vLLM or TGI. If you are running on NVIDIA hardware, which most of the world still is, vLLM is the gold standard for high concurrency throughput. You want those paged attention benefits. You want to be able to serve 100 users on a single card instead of just 5. But if you are in a high-security environment or you have a very specific latency requirement, like high-frequency trading or real-time medical imaging, then you spend the time to implement TensorRT LLM. You go close to the metal. You pay the complexity tax to get the performance rebate.
What about the ONNX crowd? Is there still a strong case for that universal translator approach in this world of specialized chips?
Especially for enterprise software that needs to run on-premise for various clients. If you sell software to a bank, you do not know if they have a rack of NVIDIA cards or a bunch of Intel Gaudi accelerators. ONNX gives you that insurance policy. You write the implementation once, and it runs anywhere, even if it is not the fastest version possible. It is about market reach and reducing maintenance overhead.
It is funny to think that we used to just talk about the models. We would spend hours debating Llama versus Claude versus Gemini. Now, the conversation is becoming much more like traditional software engineering. It is about memory management, kernel optimization, and network routing. The AI part is almost becoming the easy part. The intelligence is a given. The execution is the challenge.
The model weights are becoming a commodity. Everyone has a great 7 billion or 70 billion parameter model now. The real competitive advantage is becoming the operational efficiency. How cheaply and how fast can you run that model? That is why the runtime is the new operating system of the AI age. It is the layer that manages the resources and provides the services that the application, the model, needs to function.
It is also worth mentioning that this connects back to what we talked about in episode 1479 about the speed of thought. As inference gets faster and cheaper, the way we interact with AI changes. We move from these long, slow prompts to these rapid-fire, agentic interactions where the AI is basically thinking in real time alongside us. We are moving from batch processing our thoughts to stream processing them.
And you cannot do that without a runtime that can handle the pressure. If you are interested in how the infrastructure above the runtime is evolving, you should definitely check out episode 841, where we talked about AI gateways and light, LLM. That is the layer that sits on top of these runtimes to handle things like failover and load balancing. It is the traffic controller for your inference fleet.
It is a whole new stack, from the GPU at the bottom, through the runtime, up to the gateway, and finally to the user. It is getting complex, but it is also getting incredibly powerful. I think the takeaway for me is that if you are still just thinking about the weights, you are only seeing half the picture. The weights are the potential energy, the runtime is the kinetic energy.
It is the difference between having a blueprint for a car and actually having an engine that can turn fuel into motion. You can have the best blueprint in the world, but if your engine is seized up, you are not going anywhere.
We are finally getting to the point where the engines are becoming reliable enough for the mass market. I am curious to see if we eventually see a consolidation here. Do you think we will end up with one runtime to rule them all, or will it stay this fragmented? Will we see a Linux of AI runtimes?
I think the fragmentation is a feature, not a bug. Hardware is diversifying. We have NPUs in phones, specialized AI chips in the cloud, and traditional GPUs. As long as the hardware stays diverse, the runtimes will have to stay diverse to squeeze the performance out of them. We might see better abstractions, like what the CNCF is doing with KAIR, but the low-level engines will always need to be specialized. You do not use a Formula One engine in a tractor, even if they both run on fuel.
Well, I, for one, am glad there are people like you who enjoy reading white papers about PagedAttention, so I do not have to. I will stick to making the jokes and asking the annoying questions. It is a division of labor that works for me.
Someone has to keep us grounded in the reality of the silicon, Herman. It is easy to get lost in the magic of AI and forget that it is all just electrons moving through gates at the end of the day.
Fair enough. I think we have given Daniel a pretty thorough breakdown of the landscape. It is a fast-moving target, especially with the news coming out of the Kubernetes world today. It feels like every week there is a new benchmark or a new standard that shifts the goalposts.
The KAIR 1.35 spec is going to change how a lot of people think about their clusters over the next few months. It is a good time to be an infrastructure nerd. We are finally getting the tools we need to build real industrial-scale AI systems.
Is there ever a bad time to be an infrastructure nerd in your world, Corn? You seem to find excitement in the most obscure configuration files.
Not since 2022, that is for sure. The pace of innovation in the plumbing of AI is just as fast as the innovation in the models themselves.
All right, let us wrap this one up. We have covered the shift to the deployment era, the difference between local and cloud runtimes, why your choice of wait format matters, and the trade-offs between flexibility and raw speed. We have looked at the new Blackwell chips, the Dynamo routing signals, and the new Kubernetes standards.
And don't forget the KV cache. Always mind your KV cache. It is the most expensive memory you own.
I will try to keep mine as unfragmented as possible, though my brain might disagree after all this technical talk. Thanks as always to our producer Hilbert Flumingtop for keeping the show running smoothly behind the scenes.
And a big thanks to Modal for providing the GPU credits that power our research and this show. Their serverless platform is actually a great example of how this runtime management can be abstracted away for developers. They handle the cold starts and the kernel optimizations, so you can just focus on the code.
This has been My Weird Prompts. If you are enjoying the deep dives into the guts of the AI revolution, search for My Weird Prompts on Telegram to get notified the second a new episode drops. We have a lot more ground to cover as we head into the rest of 2026.
We will be back soon with more explorations into the weird and wonderful world of AI. There is always another layer of the stack to peel back.
See you then.
Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the close from sloth from man, from long-eared host. My Weird Prompts, until next time, stay curious, keep weirding.